we're going to do a quick overview of some things that you know, and we're also going to look at convex and concave. Okay, so looking at things that we already know, on these two graphs, we know about minimum and maximum points. So on this first graph of x squared take away 4, we know that down here is a minimum point. Okay, and we know that it's a stationary point. Because if I was to draw a tangent to the curve, then it would be horizontal at that point. So a stationary point, we find a stationary point by setting our differential as equal to 0. And we know it's a minimum because we find our second differential, it's greater than 0 if we have a minimum. But this is a minimum point, so it's at that exact point is the minimum. Okay, so over here, same kind of principle, but up here is a maximum point. Okay, so you've got maximum point, which is also a stationary point. So we know our differential is equal to 0 because it's a stationary point. If I was to draw a tangent to a curve, it would be horizontal again. Maximum point, this time my second differential is less than 0. Okay, so hopefully we can remember why our second differential is less than 0. So going back to this graph, over here my line is sloping downwards, so my gradient is negative. So my gradient is less than 0, it's negative. Down here at this stationary point, at the minimum, my differential is equal to 0. As we've said, it's a stationary point. And over here, my differential, my gradient is increasing, so it's greater than 0. Okay, so my gradient has gone from negative to 0 to positive. So the gradient is increasing, which is why my second differential is greater than 0. But this relates to something that we're going to talk about today. So there's some key words. We've got concave and convex. Now concave is the shape of a graph if it's got a sort of N shape. And convex is a sort of U shape. Okay, and we can see that this graph of x squared take away 4 has always got a convex shape. There's no kind of sections of that graph that look like an N. Okay, so there's no kind of concave sections. So this is convex. But it's convex for every single value on our x-axis. No matter where we are on the x-axis, that graph will be convex. Okay, so that's kind of what today's, or what this lesson is kind of looking at, is finding the values for where it's concave and where it's convex. Okay, so over here, this gradient, it's positive, so dy dx is positive. At this point, my stationary point, my gradient is 0, and at this point over here, my gradient is less than 0 because it's decreasing. So it's gone from positive to 0 to negative. So the change in the gradient is decreasing, which is why my maximum points where my second differential is less than 0. But we can see for every single value on my x-axis, the graph will be concave. It will have this N shape. No matter where we are on our x-axis, it will be part of a concave curve. Okay, so we need to kind of look and see what that means, or how we show that it's concave and convex. So this is the maximum point and this is the minimum point, but that's just at one point on each graph. Okay, whereas we need to find the range of values for concave and convex. So we use the same principle, that a second differential is less than or greater to 0. Okay, so for a concave graph, we know that our second differential is less than 0. okay, because we would have a maximum point. For concave, our second differential is less than 0. And for our convex, our second differential is greater than 0. Okay. Sometimes you can have a concave and convex. So imagine a graph like this. Okay. So this part will be concave, up to about there. This part will be convex. Okay. So you've got to find which value it goes up to here until it starts to become a convex graph. So we find the range of values that it's concave and the range of values that it's convex. But a different video will talk you through a couple of examples on that. Okay, and in between concave and convex, we have a different point. So we've got our second differential is less than 0, our second differential is greater than 0. But what if it's equal to 0? And that's what we call a point of inflection. So our point of inflection always has the second differential as equal to 0. Okay, but we will come back to that. So I'm just going to show you what I mean about concave and convex with these two equations. So I've got y equals x squared take 4 and y equals negative x squared plus 4. So I'll keep the notes on the page. If I've got y equals negative x squared plus 4 and y equals x squared take 4, I find my second differential. So my first differential is negative 2x. My second differential is negative 2. Well, negative 2 is always less than 0, no matter what. Negative 2 is always less than 0. It's got no x's in. So, well, it's always less than 0. So this graph here is always concave because my second differential is less than 0 all the time, so it's always concave, which will make sense, okay? And for the next one, y equals x squared take 4, our first differential is 2x, our second differential is 2, and 2 is always greater than 0. Well, when my second differential is greater than 0, we have a convex, which is a U-shaped curve, and we can see for all values it's convex. Okay, but just to kind of show you something different, if we had y equals x cubed, okay, we know that that looks like this. So for this section we can see it's more of a concave, and for this section we can see it's more of a convex. Okay, and we know that kind of 0, 0 is an important point. So my first differential is 3x squared. My second differential is 6x. Okay, so we want to kind of find when that graph is concave and convex. Well, it's concave when 6x is less than 0, so x is less than 0, and it's convex when 6x is greater than 0 or when x is greater than 0, which completely makes sense because we've just said that this section before 0 is more concave and this section after 0, when x is greater than 0, is more convex. Okay, so that's what we kind of mean with concave and convex, but a different video will talk you through that. So now we move